All right, before we move on to the next part, I want to just point out a little error that I had in the last video that actually Nuggets pointed out, so I give credit to her. I didn't add the 0.19, or I didn't go off with the decimals. I just wrote down 114. Of course, 114.919 is more accurate. All right, so what we've been doing is we made this formula so it would be much easier to shrink our intervals of h. We can just start at 0.1, we can go to 0.01, and if I wanted, I could go even smaller, 0.001. It'd be really easy to solve because I've got this formula. So now I'm going to ask this question. What would h have to be if we moved from a secant to a tangent? Remember that what we're actually finding is a tiny little secant. That's right, Tim. So we would need the secant distance to be 0, right? We would keep shrinking h into smaller and smaller and closer to 0, to the point that it would kind of be right next to 0. In fact, we would love it to be equal to 0. So in order to move from a secant, which is a very good estimate of the slope of the tangent, or the steepness of the curve, we know that a tangent is better. And if h could get really, really close to 0, we would have a really, really good estimate. And in fact, if it was 0, we would have the actual steepness of the curve. And if our formula works, then we could actually plug in h as 0, and we would get the answer as 114. So this is the first time that we've actually been able to find the slope of a tangent legitimately, because we've shrunk our h's using this formula. We've shrunk our h's down so to a point that the h isn't a problem, and we can just plug in h is 0, and guess what? We found 114. That's the actual slope of the tangent at x equals 3. All we did before on the first few days was get really, really close, and then we would guess that it was 114, and then we'd go to Desmos and say, yep, we're right. But here is the first time we've done this math. So my question is, what's the big deal? Why wouldn't we just plug in 0 from the start? Why didn't we just plug in h equals 0 from the start? And why did we have to go through this whole formula of putting in h equals h and that sort of stuff? That's right. So Talon's just told me that the problem was, at first, we would have a 0 on the bottom. So if we did plug it in at the beginning, it would be f at 3 plus 0 minus f at 3 all over 0. So we couldn't plug in h equals 0 at the beginning because we'd be dividing by 0. Now luckily we plugged in h equals h, and then the h disappeared, right? It canceled out, and then we could sub in 0. But we kind of cheated by doing that. Even though it canceled out and that was great, because h is equal 0 someplace in the formula, technically you're not allowed to substitute it in. It's actually not in the domain because of the problem that happens early on. So even though way back here, like we're coming along here, we're not allowed, we would end up with a problem here if I plugged it in, here, all throughout this equation, there'd be issues if I plugged in 0. Just because it cancels out in this way spot down here doesn't mean okay, great, now everything's all fine and dandy. Okay? So this is the issue that we're having, and why we didn't just do this from the start. So that formula that I used to get there is really, really handy, but it's a kind of a cheat. can't explicitly use the formula like we did to find the slope of the tangent because of the issues of dividing by 0. Regardless if it cancels later on, it still is a problem. So here's the bit of a leap of faith or an understanding that we have to get to. We're actually going to be shrinking the h value so small that it is essentially 0. Okay? We're coming so close that the h value approaches, but actually doesn't ever touch 0. And so you're going to make it so small that it feels like it's 0. But of course, every time you make an h length, you can always find one smaller, right? So even if you say it's 0.000001, say, well, that's pretty much 0. Well, guess what? There's always still one smaller. So you can always get a little bit smaller, and that's a problem. So you can never actually get to 0, which is okay, because I don't want to actually get to 0, because when I get to 0, I'm dividing by 0, and it's a problem. I want to get really, really close to it without actually touching it. But know that if I'm so close to it that I'm essentially there. This idea is something called the limit. This was one of the big breakthroughs in mathematics at the time, the idea of a limit. So I'm saying that this thing is so small that we've reached the limitness of smallness that we're essentially 0. Does that make sense? We're so tiny that if I could actually reach that limit of tininess, that I would be at 0, right? But I can never actually reach that limit. I can just get as close to it as possible, right? So we're giving that mathematical idea a name. We're calling it the limit. So you're going to get as close to it. It's kind of like an asymptote. You know how you get really, really close to it? You can't actually touch the asymptote, but you know exactly where it is because we're so close to it. So as it comes really, really close to like x equals 4, you can actually call it x equals 4. You just can't touch x equals 4, right? That is called a limit. So in our case, we're going to come really, really close to without touching 0, but essentially are at 0. And that idea is called the limit. Yep. No, we're going to put a little adjustment on what we just did. Okay? So what we're going to do is still use the same formula, but we're going to put this little disclaimer on at the beginning that allows it to work perfectly. And it looks a lot like this. And this formula's got stars around it because it is the most important fundamental theory of calculus is right in this formula. You can find the slope of the tangent by finding the limit as h approaches 0 of our slope formula that we had before.